In this video, we'll talk about the empty set and cardinality. All right, so let's start with the definition. The empty set is a set that has no elements. So we'll denote this in two ways, either with a circle with a slash through it, or we can use our set notation that has these curly brackets. But if there's nothing in it, I would write my curly brackets, but with nothing inside of them. Visually, I can think of the empty set as a bag or as a box that has nothing inside of it. It's just empty, no elements inside of it. Okay, so next we're ready to define cardinality. So if a set has n elements, where n is a positive integer, then we say S is a finite set. So there are finitely many elements in it. In that case, we say the cardinality of S is n. So the cardinality represents how many elements there are inside it. And the way I notate that is we write S, we put these sort of absolute value bars around it, which mean cardinality, and then we write n. Okay, if S is not a finite set, then we call it an infinite set. So later in the course, we'll talk about how we can discuss the cardinality of infinite sets. Okay, so let's do an example. Let's let A be the set with 2 and 3 in it, and then B is this set that has the elements 1 and 7. And then it also, one of the elements within it is a set itself that has the elements 2 and 3 in it. So a little weird there, but nonetheless, B is a set. It's a collection of objects. So I'm going to practice my cardinality notation. The cardinality of A, because there's 2 elements inside it, would be 2. And visually I can see that because if I draw a box to represent A, there are 2 elements inside, 2 and 3. And when I open up the box, there are 2 things that I can reach out and grab. Okay. With the empty set, well, there's no elements in the empty set. It is just an empty box. So its cardinality would be 0. With B, oh, this one's a little weird. So if I draw a bag or a box representing B, what's inside of it is the 1, the 7, and then there is another box or another bag that has 2 things inside of it, which is there's a 2 and there's a 3 inside of it. So if I open my set that represents B, this outer box, when I pull something out of it, I can pull out one of 3 things. Either the 1, whoops, sorry. Let me go to draw mode. I can either pull out the 1 or the 7, or I can pull out this other bag, this other set that's within it. So as a result, B, its cardinality is 3. When I find the cardinality of something, when I open this outermost bag, I am not allowed to open any other bags. It's just when I open up the bag and I reach inside of it, how many things can I pull out? Which is either the 1, the 7, or this other set in this case, this other bag. Okay, so finally, what would the cardinality of, the way I read this is a set that has the empty set within it. So that means these outer curly brackets are an empty box, and then within it is the empty set, which means within it I have another empty box. So if I open up the outer box, how many things could I pull out of it? Well, 1 thing, because I can pull out the inner box. So the cardinality of this thing is 1. Okay, so it's a little weird, but nonetheless, that is what the cardinality of this would be. Okay, so let's do another example. So the question asks, is the empty set a subset of the set 1, 2, 3? And recall what it means to be a subset is S is a subset of T. That means if X is an element of S, then X has to be an element of T. So in other words, any element of the first set has to also be an element of the second set. So I'm going to solve this in 2 ways. First, let's use this definition. So what I would have to check is if I take some element of my first set, of the empty set in this case, then is that element also an element of the second set, of my set 1, 2, 3? So then is X an element of 1, 2, 3? So is that going to be true? So, well, I got to check that no matter what element I pick from the first set, is it also in the second one? But there are no elements to pick from this first set. So when I try to check this, there's nothing to check. There is nothing to check here. Okay, so as a result, this rule that I need to be true, it's fine. There's essentially nothing to check, so it's all good. And what that means is this statement is actually what's called vacuously vacuously true, which just kind of means there's nothing to check. Another way I can see that is I have this if-then statement, and this if part says X is an element of the empty set. But that's false because there are no elements of the empty set. But if the if part is false, that automatically makes the whole thing true. That automatically makes the whole thing true, or we could say vacuously true. So as a result, is the empty set a subset of 1, 2, 3? Yes. So yes, it is. Vacuously so. Okay. So there's another way I could see this, which is instead of trying to test, well, is it a subset of 1, 2, 3? I could ask myself, well, is it not a subset of 1, 2, 3? So like, what would it take for it to not be a subset of 1, 2, 3? Well, I would need some element in the first set that is not in the second set. But there are none. There are no elements of the empty set that are not in the second one, that are not in 1, 2, 3, that are not in the set that has 1, 2, 3 in it. So as a result, this is not true. So claiming the empty set is not a subset of 1, 2, 3, well, that claim is false. That claim is false. So both of these solutions verify this claim that, oh yeah, the empty set is a subset of 1, 2, 3. So what are the takeaways from this? For any set S, the empty set is always a subset of S. And another thing I could say is S itself is always going to be a subset of S, because any element of S is also going to be an element of S.